Kia ora Year 12. This question is going to go through part C of question 10 of the November 2020 paper 32 question. Now, we've just done, as part of going over iterative methods, parts A and B of this question, but part C of this question is really nice, and it's probably the hardest question in the paper, so I've decided to video it now anyway. It uses a technique called integration by parts that we're going to be getting to quite soon, but I think a few of you probably have worked ahead and know this method already. So I'm going to do this video, and I'm not going to go super slowly through the integration by parts. I'm just going to get on with it and do it. So what we're asked to do is that we've got this function y equals root x cos x, and that's what's up here. And now we're not focusing on this minimum point anymore. We're trying to find the volume of the solid obtained when the region R here is rotated completely about the x-axis. So as soon as you see that, you should think back to AS and think, well, how do we do volumes of solids? Well, volumes of solids of revolution are pretty cool, and they're also really much easier than they sound, right? So we're taking that function and we're going to rotate it around. And the volume will be given by the integral. So say I'm doing between A and B, it'll be the integral from B to A. And then we're using, think about a whole series of disks, right? So you've got a flat surface at the end of that, and its height, oh, this is a terrible picture to explain volumes of solids. Sorry, guys. Let's back up. So the height here, suppose this is point C, height up here is f of c. And you can think of that as being the radius of your circle, just turning the picture around so that you can see that you've got a series of disks. And that means that to find the volume of a solid of revolution, I'm doing pi r squared, but my radius is just the height at each point. And that's going to change as I move along the shape. Now, I'll show you a cool GeoGebra applet for that in class when we do some revision, but that's the basic idea. So what we have to do here is we're going to take this function and we're going to square it and times it by pi. But the other thing we have to do to get going is to work out what my limits are. Now we know the first limit is going to be 0, and then we have to find the next x-intercept here. So when is that going to happen? Well, we've got root x cos x, and we need that to be 0. Now we've already found this one, which is where x is 0, and now we need to know where is cosine of x equal to 0. And the first place that that's going to happen will, of course, be at x is equal to pi on 2. So setting this up, r is equal to the integral from pi on 2 to 0 of pi times root x cos x squared dx. So there are about 10 lines of working for this whole problem, but there's a wee bit of thinking. So we'll take the pi out here, and now we've got x times cos squared of x dx. We haven't done much yet with trig integrals, but you can, if you think about it, this is not nice to integrate. It does not integrate back to cos cubed of x, or 1/3 of that, or anything like that, because when I try to differentiate this, because of the chain rule, I end up having a negative sine x popping out, right? So that's not going to work. So we don't like directly integrating trig powers. What we're going to do instead is think about our wonderful double angle formulae, because if we can use that, we can easily deal with trig integrals. So cos of 2x is the one that's going to help us. So cos of 2x is equal to 2 cos squared x minus 1. Cos of 2x plus 1 is equal to cos squared of x, and is equal to 2 cos squared of x. That gives me a half of cos of 2x plus 1/2 is equal to cos squared of x, or you could just leave the half as a factor in there. So I'm going to replace cos squared of x with this and then try and integrate. So we'll just put that in a bubble. So if you were doing that in the example, you'd do that off to the side, right? So moving on, we've got equals pi times the integral from pi on 2 to 0 of x times 1/2 cos of 2x plus 1 dx, right? So it actually is better if you just leave that half factored there. Now, we'll move we'll multiply this through the integral. So we get pi on 2 times the integral from pi on 2 to 0 of x cos of 2x plus x dx. One of those is going to be really easy and one's going to take a bit of work. So the first one, we're going to split this into two integrals. We have from pi on 2, so that's this one here, and then we're going to have the integral that's going to need integration by parts to deal with, which is going to be x times cos of 2x dx. So this first one is a level 2 integral, nothing to it. And then this one here, we have to think about, right, so integration by parts is going to be what I need here. I've got something that looks like a product, and that means I'm straight away thinking about IBP. This is going to be one where I can integrate it and it doesn't get worse, but if I integrate the x, it is going to get worse. I'm going to get a squared term, and then it's going to spiral, not out of control, but it's going to keep going from there. So this is going to be the function that I leave, and this is going to be the function that I integrate. And in the second half of the IBP, this will be the one that I differentiate, and this stays the one that I integrate. Now you'll get used to spotting which one goes where, but the nice thing that's going to happen is that in the integral part of the IBP, this is going to differentiate to 1, leaving me with a really easy to integrate thing. The biggest thing that's going to go wrong from here is probably that you make mistakes with signs. So be really, really careful with your working. So it's going to be plus, and then I'm going to do it on a new line. So we're going to have pi on 2 times x times the integral of this, which will be 1/2 sine of 2x, evaluated at my integral limits. Now it's worth at this point, I think for most of you, checking back that you have not mucked up that integration. So let's just differentiate this back and make sure that we're going well. So sine differentiates to cosine, so this will be cosine 2x, and the chain rule is going to give me a 2, which I don't want, so I undo it with the half. So that's looking good. Minus the integral from pi on 2 to 0, and this time I differentiate this, so it's going to be 1 times 1/2 sine 2x dx. Right, so let's figure out this thing here and get going on the rest. We've got pi on 2 times pi squared on 8. So I'm doing this bit here now. So pi squared on 8 minus 0 plus pi on 2. Now I'm going to evaluate this one. Now sine of pi is 0. So it's easy, this one. It's going to be pi on 2 times 1/2 times 0 minus 0. Now I'm going to have minus pi on 2 times this integral. So notice how many steps I'm doing this working in, and this is to reduce errors because we've done a lot of work to get to this point. We've done 8.5 minutes of video already. So this one here works out to be pi cubed on 16. This is 0. Now I've got minus pi on 4. Right, again, multiplying my constant through. So pi on 4 times the integral of sine 2x. So sine 2x has come from a cosine of 2x, but I need a negative sign to undo the negative when I differentiate, and I need to multiply it by 1/2. Hopefully if you're watching this early, you can see how much practice you've got to get fluent in doing these IBP questions. So we've got pi cubed on 16, and now I've got plus pi on 8 times cosine of pi minus cosine of 0. Pi cubed on 16 plus pi on 8 times -1 minus 1. Just about there. Pi cubed on 16 minus 2 pi on 8, which is pi on 4. Now, it's fine to leave your answer like that. That would definitely get full marks. If you want to do what they did in the schedule, you can factor out a pi on 16, and then you get pi squared minus 4. So I don't know about you, but it's pretty cool seeing pi cubed coming up in that question. Not that common, but there you go. Right, and that was a very long video. If anyone has actually watched to the end, there will be a chocolate prize. And Sam Newdick, if you're watching, I promise this time I actually will deliver the chocolate prize. Thanks.